Hello, my name is Long Q. I'm a research scientist at KAUST. In this talk, I will show you our first experiments on ACC for FX using our own developed stencil library, Geary. By the end of the talk, you will learn the performance of MWDTB stencil, which is a newly developed temporal blocking technology on ACC for FX. For your information, MWDTB can be plugged into specific application like reverse time migration. Here, we show a preliminary result of migrated image using MWDTB-based RTM. Here is the outline of my talk. After a short introduction, I will go through the two different stencil techniques in Geary, the classical spatial blocking and the multi-waveform diamond tiling temporal blocking, MWTTB. I will then show you some preliminary results of Geary on ACC4FX, and my talk will end with a conclusion and a discussion. Geary is a tool to develop and analyze the performance of multi-core waveform diamond tiling techniques for various stencil operators. We focus in this work on 3D finite difference time domain stencil with 8th order in space and 2nd order in time and constant coefficient. This stencil is a good reference as it is used in 2nd order 3D acoustic wave equation. As shown on the right, such scheme requires 8 neighboring grid points to the central point along each Cartesian direction. As stencil applications like RTM grow through all stencil grid points one time step after another, for each time step, it accesses all grid points via 3 nested loops and performs computations. To enable parallelism on multi-core architectures, one may include OpenMP directives to parallelize these loops and take advantage of the cache. On multi-core architecture in general, it is beneficial to implement cache blocking to work around memory bandwidth limitations and to increase performance. The spatial blocking is the most widely used technique in stencil computation for its simplicity and flexibility. Figures below illustrate the data reuse of spatial blocking applied to stencil computations in 1D, 2D, and 3D cases. And for a big 3D domain, we can tie it to multiple 3D cube blocks and compute them with different threads using OpenMP. Figures here illustrate with 6 OpenMP threads. The workload of each thread is shown in different color. Temporal blocking is a performance optimization technique that aims to reduce the memory bandwidth requirement of stencil computations by increasing its cache reuses within the successive time steps. MWTB refers to multi-core waveform diamond tiling temporal blocking technique, is a new temporal blocking scheme for improving the performance of stencil computations on multi-core architectures. Besides the reduction of memory bandwidth pressure, MWTB also allows overlapping computation and communication. Diamond tiling is a well-studied temporal blocking technique. The figure here illustrates its basic idea of its application in 1D grid. The horizontal axis Y is the 1D domain. The vertical axis is the time step axis. Each diamond tie has dependency to the 2 ties below as indicated by the arrows. As the diamond tiling is used in the outer dimension in our case, we use a 2-level nested OpenMP and the dynamic scheduling of the computation of different diamond ties with different group of threads. This gives flexibility in terms of assigning parallel resources, since one can choose the size of the thread group and the number of group threads that compute simultaneously. Waveform temporal blocking is another technique we use. As you see in the figure below, waveform ties are computed in order from left to right. By ensuring the waveform tie fits into cache memory, the update order in this technique maximizes the reuse of the most recently visited grid cells. Here's a figure that illustrates a 3D view of different waveform steps, combining with diamond tiling technique. Each waveform diamond tiling step is computed using multiple threads running on multiple cores, sharing a cache level. As a result, the memory bandwidth pressure can be reduced. Figures here show a 3D view of one waveform step where each thread's updates are denoted by a different color. As you can see here, each thread is assigned to one or multiple consecutive time steps of one or multiple positions in Z direction. Threads compute distribution is mainly in Z direction, and up to 2 threads in the Y direction can be used as well, since it's symmetricity. By ensuring the length of the waveform step to be the multiple of the number of threads sharing the work in the waveform direction, we can thus generate a well-balanced workload among all these threads. The memory requirement of running MWTB-based stencil computation is exactly the same as that from spatial blocking approach. Only two arrays for saving the two previous time step t and t-1 are used. After computation, the array which holds the time step t-1 will be updated to the time step t+1. We then alternate the use of these two arrays as an input and output to compute all the time steps of stencils within the diamond. Once the diamond is processed, these two arrays only save the latest two time steps of each stencil following the shape of the diamond. These curves here represent the performance of a node in terms of the gigastencil per second. For multi-thread performance on a node, MWTB beats SB in terms of the scalability and the performance for pure stencil performance on various architectures, including recent Intel and AMD chips. We also evaluate how MWTB scales on A64FX compared to Intel's Cascade Lake and AMD EPIC Rome. This figure here represents the scaling of MWTB stencil performance on these chips. We have different number of cores on the chip that we use. For AMD EPIC Rome, we use 2-socket 128-core node. For Intel Cascade Lake, we use 2-socket 48-core node. 40-core node. And for A64FX, we use single-socket 48-core node. As you can see, AMD EPIC Rome shows good performance with 128 cores. A64FX shows similar performance than single-socket EPIC Rome. But A64FX has only 48 cores compared to single-socket EPIC Rome, which has 64 cores. For Intel Cascade Lake, it shows better performance with 20 cores, but saturates quickly with larger number of cores due to the limitation of bandwidth. We also compared the performance between spatial blocking and MWTB on A64FX. We start with single-thread performance comparison. Although on A64FX, MWTB has lower L2 miss and a lower memory throughput peak ratio, as you can see in the figure below, spatial blocking is much faster than MWTB. In terms of architecture, A64FX is composed with 4 core memory groups, noted CMG. The last level cache is only shared among cores inside the same core memory groups. The volume of that is 8 megabyte. Each CMG is linked directly to its 8 gigabyte local high bandwidth memory. For this reason, we also compare both stencil techniques on a single CMG, which means 12 cores of A64FX. Due to the limitation of L2 cache inside a single CMG, we can only set up very small diamonds for MWTB. Although MWTB performs much better, but it still cannot beat SB. On all 48 cores, we see the best configuration for spatial blocking is to use 1 MPI process on each CMG. That is using 4 MPI process in all to reach 22.4 gigastencils per second. MWTB in Geary is much lower, as its performance using multi-MPI processors need to be improved as well. In this talk, we present our first Geary evaluation on A64FX. As A64FX is composed of 4 core memory group, CMG, for NUMA domains, 1 MPI process on each CMG is preferred to achieve higher performance. Compared to Intel and AMD chips, on A64FX, the classic spatial blocking performance is impressive with a good scalability. Further analysis shows it is even cache-bounded. MWTB, however, does not provide better performance than SB on A64FX. The 8 megabyte L2 cache may be small to make MWTB competitive. Also, communication layer of multi-MPI run in Geary need to be improved as well. Our recent studies also show that another potential factor making TB slower than SB is the floating point load memory access weight. In spatial blocking calculation, hardware prefetching function load most of data from memory without degrading the calculation performance, which is indeed not the case for MWTB. Our further work will be to investigate on these aspects. That's all for our first experiment of GIRI on ACC4FX. Thanks for your attention.